Hello, and welcome to our next lesson based on curricular outcome algebra and number 2, specifically looking at ordering irrational numbers. That's as in putting them in order, not telling them what to do. So first we are going to look at our curricular outcomes. Then we're going to review some number sets, talk about the irrational numbers in more detail, and then on to the examples and exercises. So our outcomes. The main outcome is that we're going to demonstrate an understanding of irrational numbers by representing, identifying, and simplifying irrational numbers, and by putting them in order. Our technology outcome here. The technology outcome is to investigate and solve problems of organization and manipulation of information. We're also going to manipulate data by using charting and graphing technologies in order to test inferences and probabilities. Long story short, what we're doing is using the calculators to help us in some of these cases. So, reviewing real number sets. We have a few common sets. One is the natural numbers. These are the numbers you get with 1 and things where you can add 1 to an existing natural number. So that gives us 1, 2, 3, 4, 5, and so on. It does not go less than 1 because we start with 1 and then we just keep adding to it. You can't hit fractions, so 3.5 is not a natural number. Whole numbers. These are very similar to the natural numbers, except they start at 0. It's worth noting that the whole numbers and natural numbers, these are Western definitions. In a lot of the eastern half of the world, they don't deal with whole numbers. The natural numbers start at 0, which is actually very sensible from a set theory perspective. Next, we have integers. Alberta's current high school curriculum uses a capital letter I for integer. Z is where it's used in the real world. The new draft of junior high also uses Z, so I'm hopeful that future incarnations of Alberta's high school will switch to Z. It's a long story short, involved political. Z comes from the German name for numbers, the Zahlen, and North American schools dropped that quote-unquote German notation in favor of an I back as a result of the World Wars. They found it was easier to remember, so they stuck with it. It just causes confusion in first-year university when students are saying I, teachers are saying Z. The students don't know what the teachers mean, and because there is another set labeled I, the teachers don't understand what the students are trying to say. Anyway, all that said, I will be trying to stick with Z. You might see I. But the integers are the whole numbers and their negatives. So -5, -4, -3, going as far as we need in either direction. Now, going in order of how we define numbers, the next would be the rational numbers. They get the symbol Q for quotient, because these are the numbers that can be expressed as fractions. That includes all of the integers, because 3 could be 3 over 1. But also the halves, the thirds, the 2/3. So we see that I have them written here not in numerical order, but in an order where numerator and denominator add up to 1, then 2, then 3, then 4, positives and negatives together. This sort of pattern can continue indefinitely. Next, I'm going to define the real numbers. So these are any numbers you could put on the number line. So that's all of the rational numbers plus all the gaps in between the rational numbers for things like pi and the square root of 2 that can't be written as fractions. The irrational numbers are the numbers that we need to fill in those gaps. So this is any real number that's not rational. So this is the set that includes pi and the square root of 2 and so on and so forth. All right, let's look at these irrational numbers in more detail. While rational numbers can be represented as fractions, terminating decimals, and repeating decimals, the irrational numbers, which you could define and are officially defined as all real numbers that are not rational, well, they can't be represented this way. So they cannot be expressed as fractions, at least not between two integers. And when you write them in decimal form, they are non-terminating and non-repeating. The irrational numbers include pi, square roots of imperfect squares, cube roots of imperfect cubes, and others, including some we have no written representation for. So decimal approximations are useful for sorting and placing them on number lines. Now, I say decimal approximations. These are non-terminating, non-repeating decimals. Because of that, we can never write them exactly on paper. We can't use just more and more decimal places because we'll never run out of decimal places. So using the decimal approximations is something that's enough to sort it. You have infinitely many non-terminating, non-repeating decimal places here. But maybe you only have to get 7 decimal places in before you know whether it is greater than or less than every number you're comparing it to. That's the key. So we approximate with decimals. Now, a little bit of an enrichment, nowhere close to the provincial curriculum. But there are way, way, way more irrational numbers than rational. Some infinities are bigger than others. So if this aleph subscript 0 is how many rational numbers there are, and there are infinitely many, then 2 to the exponent aleph 0 is how many irrational numbers there are. If you've ever seen a graph of 2 to the x, you'll know that gets very steep very fast. Now with an infinite exponent, it's huge. It is so large, I genuinely doubt that the human brain can wrap itself around how big that number is. All right, examples. So let's put these in numerical order. We've got pi, the square root of 2, and the cube root of 10. So calculators are allowed in this course. I'm assuming that we're just going to use the calculators to get an approximation for it. You could get other approximations. For example, 1 squared is 1, 2 squared is 4. We know then the square root of 2 has to be between square root of 1 and square root of 4. So we can check to see which is closer to 2 when we square it. 1.1, 1.2, 1.3, 1.4, 1.5. Square those one at a time, see which is closer. Then go to the hundredths place, find it to the nearest hundredth. Then the thousandths place, and so on. For now, we're going to use decimal approximations. So pi is roughly 3.14. The square root of 2 is roughly 1.414. And the cube root of 10 is roughly 2.1544. So now we have integers these all fit between. 1 before 2 before 3. So the square root of 2 is the lowest, starts with a 1, then the cube root of 10, and then pi. Now let's put these in numerical order. It's not hard to see that the square root of 19 will have to be greater than the square root of 17. They're both square roots. Square roots increase that way. They stay in order. The real question is, where does the cube root of 74 fit? So square root of 17 is about 4.123. 19, about 4.35889. The cube root of 74 is about 4.198. We can continue from there, but we know as soon as we get to the 4.1, it is less than the square root of 19. The fact that we follow it with a 9, that's greater than 2. So the cube root of 17 is greater, the cube root of 74 is greater than the square root of 17. So that allows us to put that in between these two. Now let's put these in order. Now we have a square, a cube, and a fourth root. So we're going to have to check these one at a time. We can see root 33. 33 is between 25 and 36. So this will be between 5 and 6. Cube roots are not as obvious. With practice, with exposure, you will learn that 5 cubed is 125 and 6 cubed is 216. So these are both between 5 and 6. And the fourth root of 1025 will also be somewhere in this range. So the root 33 is about 5.7445. Cube root of 190, that's a match to the tens place and the hundredths. It's the thousandths place where we see which one is higher. Our fourth root here, that is actually the lowest of the bunch. So that's 5.658. So we got them in almost reverse order. We start with the fourth root of 1025. We end with the cube root of 190. All right, here's some for you to practice. Put these in numerical order. So use your calculators to generate decimal approximations and then sort them out. Pause now and take whatever time you need. So the fifth root of 44,370 is less than the cube root of 636, which is less than the square root of 75. Now arrange these in numerical order. Root 63, cube root of 513, and the fourth root of 4095. Pause now and take whatever time you need. All right, so these, root 63 is the lowest. We just had to rearrange the second and third. Now, our third one, arrange these in numerical order. Cube root of 132, fourth root of 677, fifth root of 3,802. So these we got in order the first time. In summary, irrational numbers are non-terminating and non-repeating when written in their decimal approximations. To put them in order, we find the approximate decimal values to as many decimal places as required, just to tell them apart. And then you sort them like the decimal places only went that far and then terminated. Calculators can be used to assist in finding these decimal approximations. This is one of the skills where that tech is expected in our curricular outcomes. So from here, if you have any questions, any feedback, please leave them in the comments, and I will try to respond in a reasonable amount of time. I'll try to get that answered fairly quickly. So in the meantime, thank you, and watch for the next lesson.